So, yeah, good morning, everyone. Hi, I'm Sebastian. I'm from ETH Zurich, and I work together with Andreas Fichtner. And today I will be presenting my project that is using full-waveform inversion for DAS data. And full-waveform inversion has been successfully applied on global scales, for example, to find velocity models that look sort of like this, that explain a lot of observations. But of course, with DAS, we look at entirely different scales. I think I should give a short overview of how full-waveform inversion works. So we are trying to invert for the subsurface model, so for the velocities and the densities in the ground. And usually you would start off with an initial model. In this case, could be like a homogeneous model, for example. Then you start off by numerical simulations for events. So have propagating the wave field through the medium, get some synthetic measurements at receivers. You compare those measurements to actual observations by the means of some sort of misfit function. You can then plug this misfit back into the system at the point of the receiver, which is called the adjoint simulation. So this is an additional simulation you can do. And then by the magic of the adjoint method, you can combine the knowledge from the forward and the adjoint wave fields to somehow derive a model gradient if you have multiple events and receivers. And this entire process is iterative, so you would repeat this again and again, and your misfits should decrease over time until you converge. But of course, we have an entirely different setup in DAS data, so instead of having these isolated receivers, we move to more of a DAS line, and there are some things that change in that regard. So we also have different measurements, so no ground displacements anymore, but rather strain. No 3D measurements, but instead 1D measurements. Yeah, and overall, I think it's fair to say that full-waveform inversion can only be successful if your simulations are successful. So this is one of the first steps that we took, is to write sort of an extension for Salvus. Salvus is a spectral element wave propagation solver that was developed at ETH. And we wrote up an extension package where it was easier to process DAS data and to simulate DAS data. One of the advantages, for example, is that we could plug in a DAS line just by giving it coordinates, and then it's placed better inside the mesh at the collocation points. And it's sort of continuous as far as, well, it can be continuous in a computational setup. It can also be combined with topography, as you can see here. And how we get then to strain rates is by storing the displacement wave field around the DAS line, sort of in the tube. This is stored, and in an additional processing step, we would then get the strain rates along the DAS line. Yeah, but of course, I also have an application, which is the Grimsvötn Volcano in Iceland. Beautiful setting. Experiment was set in spring 2021, so I unfortunately missed that one. But as you can see, it's in the middle of Iceland. We have the caldera of the volcano right here, and this is the DAS line, overall 12 kilometers long, and the measurement went on for over a month. And because full-waveform inversion is based on actual simulating events, we first have to detect some events, so we use some STA-LTA algorithm to find events. So here, for example, you can see that there was an event happening, and using a very fancy-sounding algorithm called the probabilistic match field processing approach based on Hamiltonian Monte Carlo, we actually get some probabilistic locations that you can hopefully see in this short video, that there are events popping up. You can see down here the time, so we actually measure quite a lot of them. We have some of them that are quite shallow, where we think those are ice quakes. We have some of them that are quite deep. That's more of a volcanic tremor. And overall, we detected around 1,700 events right now. Yeah, and then we went on to simulate some of those already in a forward simulation. What kind of model to use, well, we are still not quite sure which one to use as an initial model, so we could use sort of just a homogeneous volcanic rock, one that is overlaid by some ice sheet, or we also have information about the actual ice thickness. We could also account for this. But yeah, here are some initial results for inversion for simulations. So these here would be the actual observations. These here are the forward simulations. I think the fit overall can be better. That is because we didn't do any inversions yet, so we don't know how the model actually looks like. But at least the simulations sort of pop up, so the fields here pop up at the right position along the line. Yeah, so yeah, this is my project. So we want to formulate this full waveform inversion algorithm in a general way, and then use it to image the Grimsvötn volcano. And there's still, of course, some challenges to overcome until we get there. So we can think about defining a proper misfit function, for example. We're still struggling right now to incorporate the adjoint sources, actually, but we'll figure this out. And yeah, I didn't mention that we will probably run this as a joint inversion for sources and the model itself, because there's quite some uncertainty on where the sources are actually located. So we may maybe do one iteration for the model, one iteration for the sources. Yeah, all right. Yeah, thank you very much.
Questions?